Now in the previous lecture, we have learned how can we traverse a binary search tree in 4 cases. Now in this lecture, we will look at how can we search for a node in a binary search tree. Now we know from definition of the binary search tree that on the left subtree, we have elements which are smaller and equal to the root node value. And on the right subtree, we have elements which are bigger than the value of root node in this case. This means that when we are looking for a value in each step, we will compare it with the root node's value, and based on this, we will continue to the left subtree or right subtree. So this makes our search faster. So let's say we have a binary tree like this, and we want to search for value of 40 over here. Now the first step that we are going to do over here is we are going to compare 40 with root node over here. Now we see that our root node is 70 and 40 is less than 70. So this means that we can eliminate right subtree, we can continue to the left subtree. Then we are going to continue to the left subtree, so then we are going to check it with the left child over here. Now in the left child we have 50 and we are looking for 40, so it's obvious that 40 is less than 50, so this means that we are going to continue to the left child of this subtree over here. Now when we continue to the left child of this subtree over here, we see that in the left child we have 30. So we are comparing 30 with 40, we see that 40 is greater than 30. So in this case, we have to continue to the right child. So we are going to continue to the right child. So when we reach the right child, we see that in the right child, we have 40. So 40 equals to 40. So this means that this 40 exists in our binary search tree over here. So we are going to return success. Now, if we reach the end of this tree and we couldn't find the node that we are looking for, in this case, we are returning that this node does not exist in this binary search tree over here. Now based on this logic, we are going to create search method in Java. Now here again, we are going to create search method inside binary search tree class that we created before. So our method will be like this. So it's going to return the type of binary node and the name of method will be search. So this method will take 2 parameters. The first parameter will be binary node, will be the type of binary node, and the second parameter will be the integer value, because in this case our binary search tree is integer, so this means that we are going to look for value of integer. Now then, the first thing that we are going to do in this method is we are going to check that if the node is equal to null, in this case we are going to return that the value does not found in this binary search tree over here. So I'm going to put first if condition like this. If node that comes from this parameter is equal to null, in this case it means that the value that we are looking for does not exist in this binary search tree over here. So I'm going to print out to the console saying that value, so I'm just going to concatenate the value that we are getting from the parameter not found in binary search tree. Then after doing so, in this case we are going to return null. Then in the else if condition, we are going to check the node's value with the value that we are looking for. So if they are equal, it means that this value exists in our binary search tree over here. So I'm going to put it like this. Else if node.value is equal to value that we are looking for, in this case it means that this value exists in this binary search tree over here. So this means that I'm just going to print out to the console this message. So I'm just going to copy it from here. Value, instead of not, I'm just going to put found in binary search tree. Then after doing so, we need to return this node. So because our method returns the type of binary node, so in this case I'm just going to return node. Now then we might have cases that if the node value is not equal to value that we are looking for, so this means that it might be less or greater than this node value over here. So if it is less, it means that we are going to continue to the left subtree. If it is greater, it means that we are going to continue to the right subtree. So that's why I'm going to put our else if condition like this. Else if value less than node.value, this means that we are going to call this method recursively for left subtree. So I'm just going to put return search. So it's going to be called for node.left with the same value. Now in the else condition, we are going to call this method for right child, because if it is not less than the node value, it means that it's greater than the node value. So in the else condition, we are going to call it for right child. So with this, we have completed our methods. Basically what we are doing over here is, first we are checking that if the node is equal to null, it means that this value does not exist in our binary search tree, so we are going to return null. So otherwise, we have created a base condition for recursive calls over here, so in which we are checking the node value with the value. So if the node value is equal to value, this means that we have found our node in our binary search tree. Otherwise, we are going to continue to the left or right subtree by comparing node value with the value that we are looking for. So if it is less than the node value, it means that we are going to continue to the left subtree. If it is greater than the node value, it means that we are going to continue to the right subtree. Now let's see how this is working in practice. So inside main class, we have created our binary search tree like this. So I'm just going to call search method. So it's going to take basically two parameters. So first parameter will be root, and the second parameter will be, for example, let's say we are looking for value of 40. So we know that 40 exists in this binary search tree over here. So this means that this method should print out to the console saying that 40 exists in this binary search tree over here. So let's run our code. Now after running our method, you see that it's printing out to the console that the value 40 found in this binary search tree over here. For example, if I search for 45, in this case 45 does not exist in this binary search tree over here. It's printing out that value 45 not found in this binary search tree over here. So this means that our search method works the way that it should be. Now let's look at what's the time and space complexity for this method over here. Now as always, we are going to start from the first line of this method. So in the first line, we are checking if node is equal to null. In this case, we are printing out message to the console, then returning null. So this part of if condition will take O1 time complexity because each line over here takes O1 time complexity. Then in the else if condition, we are checking that if the node value is equal to the value, in this case, we are printing out to the console that the value exists in our binary search tree. So then we are returning node over here. So this part of code also will take O1 time complexity because each line over here also takes O1 time complexity. Now then in the else if condition, we are checking if the value that we are looking for is less than node value. So this line of code will take O1 time complexity. Then if it is less than the node value, we are calling this method recursively for left subtree. So in this case, this code will take O(n) divided by 2 time complexity. Then in the else condition, we are calling it for the right child. So this one also will take O(n) divided by 2 time complexity. Now if we combine all these complexities over here, we get O log n time complexity. Because in this case, we are going to call it for just left or right subtree. So that's why the time complexity is O log n time complexity. Now the space complexity is also O log n because in this case, when we are calling method recursively for either left or right child, we are going to insert the elements to the stack memory. So that's why the space complexity is O log n. Now with this, we have come to the end of this lecture. So in this lecture, we have learned how can we search for a node in binary search tree. So hopefully everything is clear about this lecture. So see you in the next lecture.